Alright, thanks for watching, and today we'll do something really cool. We will find the derivative of a function, but in higher dimensions. It's something that's called partial derivatives, which is partially derivative, but a whole lot of fun. So, consider the following function. The function f of xy, which is x squared y plus xy squared. And our goal is to find the derivative of f, whatever that means. Now, the issue is f depends on two variables. So you might say there's no way to find a derivative, but yes there is, provided that you differentiate with respect to each variable separately. And that is what's called a partial derivative. So intuitively, and I'll give you a definition at the end, intuitively, there's something called fx, or also written as partial f over partial x. And what this is, it's the partial derivative of f with respect to x. And what does that mean? It just means differentiate f with respect to x, but leave y constant. So for instance here, again we have f of xy is x squared y plus xy squared. And what is fx here in this case? What this means in this expression, you only differentiate x squared and y becomes a constant. So fx, in that case, becomes 2xy, and then you differentiate this with respect to x, so just with respect to that variable, so it becomes 1 times y squared. And that, in the end, you get 2xy plus y squared. Well, that is the derivative of f with respect to x, but of course you can do the same thing with respect to y. So fy, again, that's partial f over partial y. What this is, it's the partial derivative of f with respect to y. So in that case, you still take f, but now you let x be constant and you differentiate with respect to y. So fyi, very important, you just take this function and differentiate with respect to y. So x squared is constant, but now the derivative of y is 1. And you leave x constant again, and you differentiate y squared to get 2y. And in the end, you get x squared plus 2xy. Now, of course, here I did it very slowly, but in practice, you can do it more quickly. For instance, if f is this, x to the 4th plus 5xy cubed, then fx is just this with respect to x, so x to the 4th plus 5xy cubed, x. And again, you just take all your x's and differentiate with respect to x. So this becomes 4x cubed plus 5y cubed. And you can also do this with respect to y. So then fy, that's x to the 4th plus 5xy cubed with respect to y. Well, the only y here is in y cubed, so if you differentiate this with respect to y, you get 0, and then you get 5x, and then 3y squared, and we get, I think, 15xy squared. And of course, not only that, but if f depends on 3 variables, you can differentiate with respect to every variable here. So for instance, take f of xyz, that is x e to the yz. And then what you can do, you can find the partial derivative with respect to x, with respect to y, and with respect to z. So fx is the derivative of, again very careful, x e to the yz with respect to x, which becomes e to the yz. On the other hand, you have fy, which is, again, the derivative of x e to the yz, z with respect to y. And look, x here becomes a constant with respect to y, so we leave it alone. And then we differentiate e to the yz, and here z is constant. So you have to think of it as like almost like e to the 3y. So what this becomes, it's e to the yz times z, if you want y times 3 or something. So times, in this case, times z, and you get xz e to the yz. And you can continue, fz becomes the derivative of x e to the y z with respect to z. Again, think of e to the yz now as being e to the 3z or something. X still becomes x, okay? And then you differentiate e to the yz. Well, if you differentiate this with respect to z, this y comes out. E to the yz times y, and we get xy e to the yz. And of course, no matter what functions you have, you can really differentiate with respect to each variable. And, well, just like for ordinary derivatives, you can also differentiate a function at a certain point. And what's nice about that is that we can give a very nice graphical interpretation of this. So fourth example, take f of xy be y squared minus x squared. And the question is, find the derivatives at the point 1, 2. So fx 1, 2 and fy at 1, 2. Well, just like f prime, you first differentiate f and then you plug in the point. So fx in this case becomes, well, if you differentiate that with respect to x, you get minus 2x. So in particular, if you plug in the point 1, 2, you get, all this means is x equals 1 and y equals 2. So you get minus 2 times 1, which is minus 2. So in other words, the derivative of f with respect to x is minus 2. And similarly, the derivative of f with respect to y, here you get 2y minus 0, which is 2y. So in particular, at the particular point, you get 2 times 2, which is 4. Okay, so in other words, with this particular function, the derivative of f with respect to x at the point is minus 2, and with respect to y at that point is 4. Now, what does that mean graphically? So let's look at this function in more detail. So it's one of the most hated mathematical figures, unfortunately, is what's called a saddle, or an, I believe, a hyperbolic paraboloid, because it almost looks like the parabola, hyperbola, sorry, y squared minus x squared equals 1. So let me just remind yourself what this looks like. Well, with respect to y, it looks like the parabola that goes down and then up. But with respect to x, it looks like the parabola that goes up and then down. So kinda, in this direction, it just curves downwards, like that. But in the x direction, it curves downwards in this case. So this is roughly, more or less, the this hyperbolic paraboloid. So y squared minus x squared. And we're particularly focusing on the point 1, 2, which looks somewhere like that. So maybe you go up here at this point, whatever f of 1, 2 is, and notice what is happening here. Well, this function more or less has two main directions, the y direction and the x direction. And notice there's something interesting happening. In the x direction, so here, the function moves downwards. On the other hand, in the y direction, the function moves upwards. So we have those two kind of different phenomena happening, and more precisely, the function goes downwards at a certain rate and goes upwards at another certain rate. And those rates are precisely the partial derivatives. So the fact that fx at that point is minus 2, all that this means is that the slope at this point, in the x direction, it's minus 2. On the other hand, the fact that fy is 4 means that in the y direction, the slope is actually 4. And in fact, that is the precise definition of the partial derivative. All that this is, fx is just the slope of the tangent line in the x direction. So in this case, minus 2. And fy is the slope of the tangent line in the y direction. So, in other words, let me just write this down. So fx at 1, 2 is just the slope of the tangent line of f at 1, 2 in the x direction, and fy at 1, 2. It's the same thing, but in the y direction. And the nice thing is, using this graphical interpretation, we can finally give an actual definition of the partial derivatives, which is more or less just based on this picture, which I'll erase and then redraw. So again, you have your function f, which looks something like that. Again, so this is f. On the other hand, you have the point 1, 2. And if you go up, take the elevator up, you have f of 1, 2. As I said, fx is the slope of the tangent line in the x direction. So kind of like here. And what this means is, more precisely, you start at the point 1, 2 and go a little bit forward in the x direction to get some point 1 plus h, 2, where h is very small. And if you go up with f here, you get the point f of 1 plus h, 2. And what this gives you is what's called a secant line, just in calculus. Okay. And the slope of that secant line, so okay, we're almost at fx at 1, 2. The slope of that secant line, just like in ordinary calculus, is f of 1 plus h, 2, minus f of 1, 2 over h. And then all you do, you let h to be very small. So in other words, you take the limit as h goes to 0 of the slopes of the secant line, but in the x direction. And of course, you may guess what happens in the y direction. This time, you just take a little increment, but in the y direction. So you take 1, comma, 2 plus h. And if you go up with f, you get f of 1, comma, 2 plus h. In the y direction. And you also take the slope of that secant line, which goes like that. And again, you may guess that fy at 1, 2, it's again, same thing as before, you take the limit as h goes to 0 of f of 1, comma, 2 plus h minus f of 1, comma, 2 over h. And this is the precise definition of the partial derivative. So just be careful, there's this difference between just computing it, between letting x or y be constant, and the actual definition in terms of slopes of tangent lines. And last thing I want to talk about, because those partial derivatives are so addictive, you kind of want to do it again and again. So the nice thing is, you can also take second order partial derivatives, and in fact, higher order ones. So as many as you want. So for instance, consider the following function. I believe it's example 5 or something. So f of xy becomes x to the 4th plus 2x y cubed plus y to the 4th. Then, first of all, let's calculate the first order partial derivatives. So fx becomes 4x cubed plus 2y cubed. And then fy becomes, I believe, 2x 3y squared plus 4y cubed, which I think becomes 6xy squared plus 4y cubed. And of course, those are the first order partial derivatives, but now you can just continue. How about we calculate the following ones? So let's do fxx, fxy, fyx, and fyy. What does that mean? It just means do fx as a function and differentiate with respect to x. So just take this function and do the x derivative of this. So fxx, which is just 4x cubed plus 2y cubed with respect to x. And that becomes a 12x squared, I believe. And now do the same thing with respect to y. So 4x cubed plus 2y cubed y. I believe all you get is a 6y squared. And now let's do fyx. That becomes 6x y squared plus 4y cubed with respect to x. And I believe what this becomes, it becomes 6y cubed, y squared. And lastly, let's do fyy. That becomes the last one with respect to y, so 6xy squared plus 4y cubed with respect to y, and I think that becomes 12xy plus 12y squared. Now, let's look more precisely at the results that we have. And in fact, let's play a little game of memory. Which ones of those four are equal? Dum, 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 dum. So, namely those two. In other words, f of xy is f of yx. And in fact, the cool thing is, this is always true, and it's what's called Clairaut's theorem. So, Clairaut's theorem or Schwarz's theorem says f of xy equals fyx. And I say it's always true, but disclaimer, it is not always true, because there are some pathological examples where this is not true, and essentially what we need fxy and fyx need to be continuous. And in fact, there are, as I said, some very pathological examples of this. And feel free, I think there'll be a video on this. But at least in this course, we will not really talk about those kinds of functions. But what I'm saying is, at least for this course, just feel free to interchange your partial derivatives. And in fact, that's also true for higher order ones. So this implies that f of xyz is f of zyx, which is f of yzx, etc., etc. Oh, also, there's this actually city I've been driving through, and it's so mathematical, I couldn't believe it's a city, but it's the city called ZZYZX in California, and Clairaut's theorem says you can just rearrange this to become f of xyzzz. It's falling asleep in some sense. Also, by the way, very cute fact about Clairaut, Clairaut had 19 siblings, which is pretty crazy. And not only that, he published his first math paper when he was 12. So let me ask you this, what did you do when you were 12? I don't know. I learned about negative numbers, which was pretty exciting. Alright, and that is all for now. Of course, there'll be more videos on partial derivatives, but if you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much.